Good afternoon, everyone. Let me start by thanking Seb for organizing this very interesting symposium and for congratulating for this very important honor and very well deserved. And during the symposium today, I realized we have not yet published together, so we have to solve this issue as soon as possible. I'll send you a student, but I have to send you more students probably very soon. Okay, so let me tell you a bit about I will not talk about peptides. I will talk about proteins, and more specifically amyloid fibrils. And I want to tell you a bit how we use them to solve some health and environmental problems, especially in the context of supramolecular interaction with metal ions. And this is the simplest example of amino acid transition metal complexes that I could come up with. I took it from Wikipedia, so you see this is glycine with cobalt, histidine with nickel, iridium with methionine, and nickel again with cysteine, okay? And you see the metal in the center, and this is an example of metal-ligand interaction where the ligand is the amino acid, okay? And of course, it doesn't have to be so simple. In fact, it's not so simple. Most of the time, you deal with a full sequence protein, folded protein. This is our own docking simulation of a binding event. This is lead. This is fully folded beta-lactoglobulin. I will go back to this protein afterwards. And you see that, I mean, if you navigate the landscape, this docking simulation will tell you that the lead binds to the cysteine at the 1:1 residue. Of course, this is with the properly folded protein, but if you now hydrolyze, fragment the protein, and this is, for example, an hexapeptide, which is a fragment that we know occurs if you hydrolyze in a specific way the protein. You see this is strongly amyloidogenic. Now you see this is the amyloid fibers, which is just going through the plane of the slide, and you see that now all the 121 cysteine are loaded with lead, okay? So this is just to tell you that you can exploit this on a very systematic way when you go to misfolded or refolded protein to the amyloid status. And just a couple of words again about metal-ligand interaction. So there's a fairly strong interactions on the order of 10 to 100 kBt. So it's comparable to ionic. But the main difference with ionic is this is directional. So this allows you to do things that you will not be able to do with the ionic interaction. But the strength of the bond is about the same. So just to tell you a bit of a scoop that these interactions, of course, are reversible. And having introduced the interaction, I want to introduce our main player. This is beta-lactoglobulin. I've been working with this protein for almost 20 years. The reason why I like the protein is, of course, this is a model protein, but the reason why we started to work on that is because this comes from food waste. So this is the globular protein that you find in the serum, which is left after the cheese making process. So, I mean, if whatever the cheese you're talking about, you always end up with, for 1 kilogram of cheese, anything between 7 to 10 liters of serum, and this contains just below 1% this protein. So it's an animal protein, but it's very cheap, and it's very easy to separate because it comes from liquid waste. And of course, we don't use the protein as such. Now we have learned over the years to convert the protein from the native state into amyloid fibers. We do that in a very simple way. There are several ways you can do that. You can do that enzymatically if you want to have precise cleaving point. But we found that if you simply unfold it thermally and you use a fairly aggressive pH, this will just do the job. I mean, you start with a protein which is around 18,000 Dalton. If you cook it for like 5 hours at 80 degrees pH 2, this is hydrolyzed at least 3 to 5 times, and you end up with peptides of the order of 2 to 4,000. the peptides refold into cross-beta strands on a sheaths that pack on top of each other, form protofilament, and various protofilament then aggregate laterally and form mature fibril. Now, this is something that is done in a very simple, quick, and dirty way, but what you end up in the end is a polymorph of fibril. So if I would put an histogram here, you will see a log normal distribution. This is the most crowded population, but you see multi-stranded fibril. And the beauty of that is that although you go, and we have counted up to 11 or 12 protofilament, but the angle, so the pitch over the width is preserved. So the angle of the twist is constant, and because of that, even if you break down this fiber, even if it is polydispersed, the twisting power is the same. So they have very spectacular liquid crystalline features, and they do form very controlled chiral nematic phases. And if I had more time, I could spend hours on this topic, which I will not do, because as I said, I wanted to tell you what you can do in the context of useful technology when you start to exploit interactions with metal. And I want to present you 4 different technologies that we have developed in my lab over the last 10 years. And the first one I'd like to talk to you about is about water purification. So what you do is you take the same fibril I've been telling you about. Most of my talk will be based on whey, so beta-lactoglobulin. They're very robust. They have young models which is comparable to commodity plastic, so something around 2 to 4 gigapascal. You mix it with activated carbon just to increase the porosity, and you form simply membranes that they look pretty much like that. This is one of the first membrane that we had that was just about 1 centimeter large. And the carbon is there just to provide porosity, to let water going through. I mean, it's known that carbon is good to absorbing organic, but it's very bad for inorganic stuff. And we're interested in absorbing inorganic ions. So if you have, for instance, water which is polluted by heavy metal, you have one single passage and the water will get out totally clean and removed from the contaminant. This is an example. This palladium, you can see it by the color, one single step it goes through, and this water is drinking quality. And I have the scale here. So this feeding solution is 12 part per million, and you see after one single passage, you go to 0.02 part per million. So there are 3 order of magnitude. This is a log scale. So that tells you that the way, the efficiency at which you remove heavy metal ion, palladium in this case, is around 99.9%. So there is nothing magic with palladium. The thing is, if you think about water purification, it's like having 20 exchange resin, ion exchange resin working at the same time. We have 20 amino acid, so whatever the ions you're trying to capture is, you always find the right amino acid, which has a very high binding constant. These are some of the ions that we have removed. So you see, in very broad context, industrial wastewater, so all the noble metal, gold, platinum, silver, palladium here, other nickel, chromium ions that are associated to that, nuclear waste. So here I show you the uranium. This was a very complicated experiment to run, and it is radioactive. And by now we have tested all the radionuclide that undergo fission down to technetium. Technetium is the smallest element which still undergoes fission. We remove all of them with 99.9 efficiency. These are some pollutants. You see arsenic 3, arsenic 5. If you will take reverse osmosis here as a benchmark, reverse osmosis does not remove arsenic 3. You have to oxidize into arsenic 5 and then remove it, and lead and other contaminant. So this works as a very general tool, to the point that a few years ago we incorporated a startup. It's called Blue Act. Now this startup has been around for a few years and has tested that this this technology in a very broad context, because water is everywhere and in the most diverse context you can imagine. So we've been removing groundwater, surface water, electroplating, mining, tap water, household water, and always with extremely good and satisfactory results. So I think it's safe to say that this technology now, this company was incorporated 2016. It received a lot of word coverage because this was immediately after the Flint scandal, where they found they switched the water supply, and there was like several tens of ppb of lead in water. Yeah, I mean, this is starting now to save human lives around. I could give you a lot of examples, just give you one. This is a study that is very close to my heart. We ran this study just before the pandemic. We went to Peru and we explored several places on the Andean region. And we found villages or even cities where people drink water with arsenic. So now when I say arsenic, it's arsenic 3+5. We don't know about the oxidation stage. Up to 1,000 ppb. And the WHO says that the threshold is 10. So that means there are places where in Peru, people drink arsenic at 100 times the allowed concentration. Average life expectancy in this village is 43, 45 years. And by 30, women already develop skin cancer and so on. So this study tells you that if you use these very simple membranes, you can keep for like 1 kilogram of this protein, you can sustain a family for 6 months. And after 6 months, you can even regenerate the membrane, removing with the basic flashing and keep the membrane going for a longer time. So that's the first example. Another example I want to share with you is iron fortification. And let me start with this. I love this, this image. This is a TM image. You see, these are the whey, fiber, and now we're talking about nanoparticles. So what you see here is iron oxide nanoparticle is a mixture of Fe3O4, Fe2O3. So the iron has two oxidation states here. But the interesting thing is that iron deficiency is really a huge problem. There are about 2 billion people worldwide which are either iron deficient or suffering from anemia. When I started to work on this problem in the beginning, I thought that iron deficiency was a problem for developing countries, and this is actually not the case. It's really a global problem. In Europe, 1 woman out of 5 is iron deficient. In my own lab, in 15 years at ETH, I had 1 postdoc, 1 female postdoc, 1 female PhD student that had to go regularly every 6 months to the hospital to get blood transfusion. So why is such an invasive way needed to solve iron deficiency? The answer is complex, but in a couple of words, I will simply say that there are 2 different oxidation states of iron. Iron 3, iron 2. Iron 2 is the one which complex with hemoglobin, so it's the bioavailable one, but oxidized very easily into iron 3. And once you oxidize iron 2 into iron 3, it's no longer bioavailable. So it doesn't serve anything of the biological function needed for the iron. So our approach here was very simple. Is now we know how to attach ions, iron on the surface of the fibril. We now reduce iron. We want to keep it into the state of a nanoparticle. And you see this is the change. You only notice a change in color. The colloidal dispersion is fully stable. And now the idea is that when you use this hybrid through the GI tract, when you are in the pH, the pH in the stomach, the pH is low enough to dissolve totally the iron down to the iron to the ionic form. And then, of course, the enzymes will do the rest. So pepsin, here this is just after the stomach. We now know that it's pepsin plus trypsin. So you have to go through the GI tract to digest fully the organic phase, but the idea is that by the time you reach the intestine, the iron is back to the ionic form and all the peptide have been digested. And if you now check the bioavailability, you see this is the gold standard is iron sulfate, which is 100% iron 2. It cannot be used or is used, but the impact in food fortification is really strong sensorially, and many women who are under this treatment, especially if they are pregnant, they have to stop the treatment after a few days because it is a very strong compound with a horrible taste. Still serves as a benchmark, and you see the green is the fibril. You reach a bioavailability which is close to the one of iron sulfate. In this case, we're talking still about rats. And you can do the same thing with the monomer, but if you use the monomer, the surface to volume ratio is so different that you have to use a huge amount of protein to deliver the same amount of iron. So if you now do the sensorial or the impact, you see that only the fibril can meet, in some cases, this is a dosage of 2.5 milligram for 100 grams of food that are below the allowed threshold, okay? So it works well from a bioavailability point of view. It works well from the sensorial point of view. And of course, we have run extensive histological studies. So I think we have tested 15 organs, and we do see no iron accumulation. So the iron is really absorbed through the ionic form. So when this paper was published in the end, so you see the editor came up with a very provocative title, Amyloid Fibers Conquer Iron Deficiency. And it's provocative because back at that time, this is 2017, amyloids were the bad guys, right? They were associated with pathological neurodegenerative disease, systemic amyloidosis. So this, I think, is the very first example where if you switch to non-toxic amyloid food protein, you can use them to do something useful. Yet we're talking about mice, but it took me 6 more years to actually convince that there was a lot of reticence. I've been briefly working on a food company, and when I left that company for the ETH, people were telling me we will never put this compound in food. And it took me a long time to actually show that food amyloid fibers are safe ingredient. And I did it in a very, very simple way. This is still in animal model. We take the native protein, say beta-lactoglobulin, we take the amyloid, or we take lysozyme, we take the amyloid, we digest, we do a mass spectroscopy at different time points on the GI tract, and we simply see that the peptides we have from amyloids are smaller than the one we have from the protein. So they are pre-digested, they do not cross the gut, so that we don't see any sequence in the bloodstream, so that means that they're fully digested. So our conclusion was that, these are safe ingredients. Still, this was on animal, but this study for me is very important because it was just enough to convince an ethical committee to move to human. And we just completed the human studies last year. This manuscript is under review. Actually, we have heard back from the review. We're working on the revision, but you can find the unrevised version on the medical archive. We went to Thailand because Thailand is a Southeast Asia region where women are particularly exposed to iron deficiency. And we ran a study which lasted just over a month on 52 young women. And Sam was saying before about the cost of isotope. I also went broke after this study because we use 3 different types of isotope. This is the commercial, is iron 54. This is protein fiber where we have reduced the iron with ascorbic acid. Actually, this is a salt of ascorbic acid because we don't want to use sodium ascorbate, and here we use an AOH. But we use 3 different isotopes. You see iron 54, 57, and 58, and now we can give this to the 52 women, and women act as their own control. We know precisely, by looking at different isotopes on the blood, which one is the source. Okay, we just have to analyze the isotope. And when we collect, we had to ship back the serum from Thailand to ETH, and when we look at the data, we were really blown away. This is the standard I was telling you about. There is a relative absorption of 26%. This is where we stand with the best formulation, with the iron 57. We have 46%. And even this one, look, this one, you only start with 30% iron 2. Here you have 100% iron 2. You have almost the same bioavailability. Why is that? Because the protein fiber, the amino acid in the protein fibers are reducing, they are keeping the iron constantly in the iron 2 form, so that all the iron, that 2 that you start with, it will eventually be delivered and be bioavailable. We did another control. Here we use a food formulation which contains a lot of polyphenols. Polyphenols are not to quench the bioavailability of iron, and you see still in this case, of course the bioavailability goes down. It's intentional, but we still remain either above or comparable to the iron 2 sulfate. So, and now we're working hard to prepare the revision of this paper, and hopefully we'll be able to submit in a couple of weeks. So the main highlight here is that we have a formulation now available where iron is more bioavailable than iron sulfate. Another example I want to share with you is still the same ingredient, iron and amyloid fibers, but we attach the iron in a slightly different way. So you see, we use now a very sophisticated solvent, which include ethanol, PEG, and we start from a different iron salt, because what we want to do here is something slightly different. We want to attach iron as a single atom, and we want to attach it with the oxidation 2 states. And how do we know that we succeed? Well, we've done a combination of TEM and spectroscopy. First of all, from elemental TEM, we don't see any evidence of iron nanoparticle, but of course iron is there. And then from spectroscopy, this is extend the X-ray absorption fine structure by fitting. We know that the iron as a coordination number is surrounded by around 4 to 4.5 nitrogen, and we know that this is an oxidation 2 by Xanes. Okay, so by combining several techniques, we actually confirm what we wanted. That's why we start with this funny combination of solvent. Is we want to attach now iron as iron 2 on the surface of the amyloid fibers. And why is that? Because then this mimic more or less the active side of horseradish peroxidase, so we can use that as a nanozyme for oxidizing ethanol. So what we're trying to do, and first I show you the thing in vitro. So first of all, this is the formulation of the fibril. I just told you this will be the same story if we use the monomer and not the fibril, and this will be if we use a nanoparticle on top of the fiber. So this is single atom, this is a nanoparticle. Nanoparticles have lost all the activity. You see that the fibers have an enzyme activity which is about twice as much as the monomer. And what we're doing here, we're converting ethanol into acetic acid without transiting through acetaldehyde. Alcohol abuse claims more than 30 million people lives per year. And it's not really ethanol, which is the problem is acetaldehyde, which is a long-lived transient chemical to reach acetic acid, is metabolized, as we all know, in the liver. And this is what kills the liver, kills the intestine, and also what is responsible for the hangover feeling if you have too much alcohol. So it works, but to make it work, we need, of course, peroxide, okay? And I mean, you don't drink a glass of wine and a glass of peroxide. So this is something that you have to solve. And the other thing you have to solve is these fibers are digested. So how do we solve the two problems to go in vivo? First, the digestion, I mean, you just switch to a gel. Gel slows down the diffusion of the enzymes, and this is digested within 3 or more hours within the GI tract of the mice. And the peroxide, we just need that amount of peroxide to activate this reaction. So actually what we do is we do a cascade reaction. We start with glucose. We can either put glucose oxidase, or in the paper we put fibril with gold nanoparticle, which convert glucose into gluconic acid. You generate that amount of peroxide that triggered the second reaction, okay? So that's actually a cascade reaction, and then we go in vivo, and we run two types of experiment. One is in short term. We want to see the short-term behavior of how the mice react, and the other one is long-term. So what happens in the long-term consumption of alcohol. And we have 4 groups. This is a sober mice that has never seen alcohol. This is alcohol plus PBS. This is alcohol plus the same gel without the iron. Okay, this is just the protein, and this is the gel which contains the single atom iron. And let me show you some of the results. So first of all, we look how much time is needed before the mice get intoxicated and fall asleep. So this is just the tolerance time. You see that the mice which have consumed alcohol or alcohol with the hydrogel but without the iron in less than half an hour at the dose, I can't remember the dose, they fall asleep. The mice which have used our gel, they go on for about 45 minutes. Interestingly, they don't only fall asleep afterwards, they wake up much earlier. So it takes more than 200 minutes for the first two to wake up. The mice which have taken the gel with the iron, they wake up in less than 1 hour. And this is my favorite. So this is a maze experiment. So the mice are swimming in a labyrinth, in a pool. We train the mice for a week. So after a week, they know where to start and where to get out from the labyrinth. But look at the same mice after being intoxicated with alcohol. They wander around in the labyrinth. They are lost. And we have if I put the time, is the same story. Same thing with the mice which have used the same amount of alcohol with the gel without iron, and look at the mice which have taken our product. They might have one attempt wrong, but then they immediately find the path outside. Why is that? Because for 3 hours, up to 5 hours, the amount of alcohol in the blood is half. So half of the alcohol has been converted into acetic acid without going through acetaldehyde. So this is the short term, and then I said, okay, why don't we look at what happens to the organs of the mouse in the long term? And I just want to show you one image, because image counts more than 100 words. This is what we see from the slides of the liver of 4 different mice after, I think, 16 days of heavy intoxication of alcohol. This is a sober mouse. This has never consumed alcohol in the 2 weeks. This is the mice which have consumed alcohol with PBS. You see the white spots? These are damage to the tissue of the liver caused by acetaldehyde. If they use the gel without the iron, it's pretty much the same story. And this is a slide from a mouse which has used the same amount of alcohol, but with our product. And you have to agree with me that this is pretty much the same as the sober mouse. And of course, we have done that with the length of the gut, different organs, and this all consistent. So now we're working very hard to go from animal to to human. Changing a little bit the chemistry, possibly trying to avoid cascade reaction to simplify that, but we're working very hard on that. And Judge, you got just got a Pioneer Fellowship on that from the ETA, so I'm confident we should be able to switch to human within the next 18 to 24 months. Okay. Last example I want to show you is about recovering gold from e-waste. Switching back to environmental application, we are experiencing a tsunami of e-waste. Just to give you some numbers, we are producing every year 50 million tons of e-waste, okay? It's equivalent to producing each year 4,500 Eiffel Towers. And of course, there is a huge value on this e-waste. This has been calculated around 60 or plus $billion. This is just to give it, put it in context, is 3 times more the output of all the silver mines in the world, just to give you an idea of the value which is associated with that. And this is because about 7% of the gold on this planet is now found on e-waste. So of course there is a huge value, but the recycling rate is still very low, and the methods that are used are very inefficient. In Europe we're doing a bit better, but average is about 20% recycling rate of e-waste. And you know, e-waste is non-biodegradable, so I mean, it keeps accumulating. And of course, if you look at the traditional way to extract gold from mining, you really realize that it's a sin to leave 4/5 of the gold in the e-waste, because extracting gold is something which has devastating environmental impact. Just to give you some number, this is a report from the WWF a few years ago. 1 ton of gold, you have to process 100,000 tons of rocks. Okay, and the way you do that, you either use cyanide leaching or mercury amalgam. I mean, they're both extremely toxic, and the process is very expensive in terms of CO2 emission. 1 kilogram of gold is 12,000 kilogram of CO2 equivalent on the atmosphere. And of course, if you do that, I have the data for mercury. If you extract 1 ton of gold this way, you end up with 800 tons on the mercury vapors in the atmosphere. So imagine the impact this has on soil, fauna, flora, and so on. So it's clear that the circular economy of gold has to be implemented to the point that today a kilogram of gold which is recycled is slightly more expensive than a kilogram of pristine gold, because this has been recycled and because this is traceable. There is also the fact that gold which has been recycled is not illegal gold, and 1/3 of the gold around is still coming from illegal mining. So our approach to that is very simple. We're dealing with e-waste. What do? We use food waste. So again, now you know the game. We take the whey in the protein from serum. We make the amyloid. We add salt to convert it into a gel. Then we dry, either by freeze drying, that is cryogel, or we exchange with ethanol into. Then we do CO2 supercritical solvent extraction. The end story is pretty much the same. We have a dry sponge, and on the other side, we take the electronic waste, we dissolve it into aqua regia or a mixture of acidic solvent that now dissolve all the ions. Okay, it's the gold and all the other ions which are contained in the e-waste. So this is a soup of ions. I'll show you the composition in a minute. And what you do now, you put the sponge into that, you let it sit 24 hours, and what you have to do is just to extract the sponge, and the sponge can pick up about 20% of its own weight in gold. Okay, you start with waste, and you extract 20% gold. But now what I'm telling you should sound slightly suspicious, because I told you a few minutes ago that you use this protein to extract all the ions. How comes you now only extract the gold? Because what I told you before is kinetics at play. Now is thermodynamic at play. And let me tell you first that this is the case. This is the composition. This is what you dissolve, what you have in the e-waste dissolve before and after extraction. You see, yes, there is 1 part per million of gold, but look how much copper, look how much iron. So when the postdoc came to me, and said me, let's try to see what we can extract. I said, you will have mostly copper and iron. So I I was not expecting to find more gold, but then if you start to see of the extraction, and you already see that, you have an efficiency for gold which is much higher than for the other metal. So if you now burn the sponge which has been saturated with the metal and you do some analysis, I was definitely not expecting to find 90% on this gold nugget. So this is a gold nugget, it's about half a gram. We use the board from 3 computers, and the computer content of gold is average. Our mobile phone contains 5 times more than our computer. So with 5 motherboard of all computer, we could extract about half a gram of gold, and this is about 21 to 22 carats. So the way it works is the following. The sponge is of course saturated first with iron and copper, but the binding constant of gold ions is so high that even if there are 1,000 times less, they displace the other ions and they saturate the membrane. The water purification works on kinetics. This extraction method is based on thermodynamics, and we have all the binding constant, of course. And I want to show you, so that was covered by a documentary. This is only a couple of minutes by the BBC. There is some British humor that I want to share with you. So let me just share with you the view on that from a layman perspective. I hope the audio will work. Let's see.
The first thing you do is pull all the bits of metal off of your phone or your computer, and you grind it up into this powder. This is a mix of all sorts of metals like copper and gold, palladium, platinum and stuff. So how do you get the gold out? Well, the first thing you do is pour it into some pretty nasty acid. That's why I'm wearing the goggles and the gloves. It goes green because there's a lot of copper in there. But what you then do is pop this magic sponge in there. This sponge, over the course of 24 hours, attracts ions of gold more strongly than it attracts anything else that's in that solution. So about a day later, you have a sponge that's absolutely saturated with gold ions. What you do then is take the sponge out, incinerate it, and you're left with melted gold, which when it solidifies, becomes gold nuggets. So the important question is, what is your magic sponge made of? The answer is ricotta cheese.
And of course, he didn't know what ricotta cheese is. I had to explain
ricotta cheese? No way. Well, actually, yes, whey. Because whey is the liquid left over from cheese making, which can itself be made into several things like ricotta. And it just so happens that the proteins contained within this completely natural waste product bind very strongly to gold once it's been through all that nasty acid. So you're recovering e-waste using cheese waste.
Exactly. So if I had to put it into an equation, I will put waste to the square equal gold. That's what we do.
That's alchemy, man. The results they're calling aerogel, the AU being the chemical symbol for gold. Good, you're ahead of me on that one. So far, the team has ground up 20 computer motherboards and used this natural sieve for gold to pull out a 22-carat nugget weighing 450 milligrams. The team estimates that however much the process costs in energy and materials going in, you can get 50 times that value in gold coming out. Now, this type of sponge from cheese making only works with gold, but Raffaele is hoping to discover other byproducts from other industries which would remove other materials. It may be that waste products from the oil or soy industries might bind strongly to silver or palladium or even radioactive uranium and organic materials like hormones. It would all come down to finding the right proteins in the right materials and whether nature can give us all a helping hand.
In fact, we have already extracted uranium this way. So, okay, so this concludes my talk, and I want to thank my group, of course. We took this picture only beginning of the week, so you can see also in Zurich the weather was horrible. So it's only a few days old. And especially I want to thank Mohammad and Giaci for the alcohol and the gold story. And of course, Seb, congratulations again, well deserved. Well done. Thank you.